I started to record this session. This chapter, guys, is about studying the relationship between two variables, X and Y. I'm assuming all of you were exposed to algebra or intermediate algebra before, and where you learned how to find the equation of the line y equals mx plus b. The equation of the line gives you the relationship between x and y. When you say y equals 2x plus 3, that means there is a relationship between x and y. For example, if y equals x plus 6, it means if x is 1, y is 7, 1 plus 6. If x is 2, y is 8. So that means they are related. What we're gonna study this relationship in this chapter, and we're gonna learn how can we tell if the relationship between x and y is linear or not. Linear means the x and y the points seem to belong, to a certain line, so they fit on a certain line. It doesn't have to be a perfect fit, but if they look like they fit on a line, we say that there is a linear relationship between x and y, or we call it correlation. If you can see the title of the chapter, it says correlation. Regression is the equation of the line. We're going to learn also how to find the equation of the line. You don't need to do any work by hand at all. It's all going to be done using technology and using the TI-84. What I showed you last time, guys, if you put this data in L1, the X values, and if you put the Y values in L2, and you sketch, the scatter plot, the order pair X and Y, you will get something like that. You will get this kind of a plot. How many dots do I have here? 1, 2, 3, 4, 5, 6, 7, 8. And look here, 1, 2, 3, 4, 5, 6, 7, 8 order pairs. So I have 8 points there. Each point represents an X and a Y. For example, the first point here is the 5.2, the 3.3, and so on and so forth. Now, you guys, you notice that those points seem to belong to a line. If you agree with me, there is a line where some of the points, fit very close to, and this line will be something like that. They don't fit exactly on the line, but they seem to be very close to the line. And this line is called the line of best fit. So you're going to learn how to find the equation of this line. It's called the line of best fit. But you notice here, as x increases, goes to the right, what happens to the y? It goes up. So as x goes this way, as you notice, this is going up, this goes up. So there is a relationship here. And we say the relationship is positive here. What do you mean by positive? As x increases, y increases as well. But let me give you an example where the relationship is negative. If you buy a car today, and after 1 year or 2 years or 3 years or 4 years, what happens to the value of the car? Can someone tell me, please? So you buy a car today for 20,000. You want to sell it after 1 year. Can you sell it for 20,000? What do you guys think?
No.
No. So what do you think of what's going to happen to the value of the car?
It decreases.
Okay, but you guys agree that there is a relationship between the number of years you own the car and the price of the car. As the number of years increase, the value of the car decreases more and more. Do you guys agree with this statement? There is a relationship here, but the relationship is not a positive. It's a negative relationship. A negative relationship, guys, means as x increases, y decreases. And if you draw a line, it's not going to look like this line for this one. If I draw a line for the value of the car, it's going to look like this. Let me show you. I'll show you a sketch. It will be something like that. This is the beginning value of the car, and it's going to come down like this. It won't get to 0. You always can sell your car for something. So it's not going to get right to 0 right here. But it's going to be like that. It's going to go down. So This is another example. Is there a line of best fit here? Yes, there is a line of best fit. It's somewhere right here. And we will learn how to find the equation of the line of best fit. Now, guys, if you see a relationship between X and Y that looks like this, look, if I connect, just all the points, I can put them all on one line. This is called a perfect linear relationship. This is called perfect. Or it could be like this. This is also called a perfect linear relationship. So what I'm going to go over right now, how can we tell how strong the linear relationship between X and Y is? We can tell whether it is strong or weak by finding a value called R. And this R is called the sample correlation coefficient. You don't need to find it by hand. You can do it using technology. So this R is called the sample correlation coefficient. And once you find R, from the value of R, you can tell how strong or how weak the relationship. If I recall, probably I touched on this, or if I didn't, R is a value between -1 and 1. It can go as high as 1 or as low as -1. If your R is -1, that means you have a perfect negative relationship, just like this. If your R equals to 1, you will have a perfect positive linear relationship like that. Now, if R is very close to 1, you can say that there is a strong positive linear relationship between X and Y. And if R is very close to -1, very close, guys, means like -0.9, -0.95, something like that. You can say that there is strong, but not a positive, negative relationship between X and Y. When do we say that there is not much of a relationship if R is close to 0? So if R is close to 0, guys, you can say that the relationship is weak. Let me give you an example for when R is close to 0, when you get your data, something like that. You see, guys, the data is scattered all over. I cannot tell if there is a positive linear or negative linear. They don't seem to fit on one line. This is when R is close to 0. I'm not asking you here, guys, to guess the value of R. Your technology can find the value of R for you, which we're going to demonstrate in 1 second and show you how to find R. So R, again, is called the sample correlation coefficient. We use R to have an idea about the type of the relationship, whether it is a positive or negative, and whether it is a strong or weak linear relationship. Okay, so this is the first part. That's what I talked about last time. Let me just take you to the book one more time and show you some more examples and how can you tell about the value of R. Just 1 second, please. Okay, so this is a page 473. Let me show you the formula of R, guys, so you can appreciate the calculator. This is the formula to find R. It's very complicated. I used to have students do it by hand probably 7 or 8 years ago, but no more the case. So now we just input the calculator. The X and the Y are the values that are given to you about the X and Y values. So it's a lot of work, to come up with the formula, and then you will appreciate the calculator when you can see how quickly it can find R. So the correlation coefficient is a measure of the strength and the direction of a linear relationship between two variables. And the simple R, as I told you, represents the sample correlation coefficient. In chapter 9, guys, the first question I will ask you is to find R for me. So you're going to learn how to find R. Okay, look at those examples, guys. You can see here that linear relationship is perfect. I can fit all the points on one line, so R must be 1. See, it's 1. Here, it looks like a positive. As X increases, Y increases. So you can see R is 0.81. But look here, the relationship, it doesn't look like as strong as this one. Look at the value of R, it's 0.45. Okay, let me show you here. Look here, it's a perfect negative linear relationship. So look, R is -1. This looks a little bit stronger than that one, but from the negative side. So look, you're gonna see R is -0.92. Here, it's even weaker than this one. And look at the R here, it's almost 0.04. We say no correlation here. Strong negative correlation, strong positive correlation, perfect correlation right here, and perfect correlation right there. And your calculator can do a scatter plot as well to show you those dots, which we're gonna do it in one comprehensive example in a little bit. Any questions, guys, so far? We're gonna do this exercise 15 to 18 on page 482. In exercise 15 and 18, the scatter plots show the results of a survey of 20 randomly selected males, ages 24 to 35, using age as the explanatory. So let me tell you what explanatory variable is. The explanatory variable is the X variable, which is the independent variable, and the response variable is the Y variable, which is the dependent variable right here. Match each graph with the description. So for age and body temperature, guys, which graph do you think it will be the age and body temperature? For your information, your body temperature should be about 98 point something, or 98, about 98, normal body temperature. So what do you guys think? Which graph, which one of those 4 graphs represent body temperature?
18.
I agree. I heard 18. Yes, definitely, because all the temperature seems to be around 100. Below 100, you can see, guys. So A is 18. Okay. Age and balance on a student loan. Which one do you think it's going to be?
17.
Do you guys agree with 17? Yeah, you start with the very high loan right here, you see, and it's coming down with age. Eventually, you're gonna have to pay it off, guys. And this is it, yeah, 17. Age and income.
15.
Yes, it is 15 indeed, very good. As you have more experience, guys, and more seniority, you tend to earn more money, and more education, you tend to earn more money. This is an example of that. And then age and height, it should be 16. Do you notice when people start to having back problems, they need to become a little bit shorter, you know, just with age, holding a cane, not being able to walk straight, you know, standing up straight. So that's the example right there. It looks like pretty much a flat, but it looks like it also can go down a few inches down. So this is an example, guys, of scatter plots and how you can use a scatter plot to represent a situation. Okay, so the next step, guys, we're gonna go to a comprehensive problem that has everything you need to know about this chapter from A to Z. So I'm gonna give you this example in a second. Just 1 second. Okay. So as I said, example 1, guys, is going to cover everything that you need to know in chapter 9 and all the questions that you might see on the final exam from chapter 9. I can assure you of that. So we have let X represent the age of child in years, and let Y be the number of irrelevant responses on a standardized test appropriate for the child's age. You can see, you tend to agree, guys, that if the child, you know, just is very young, it's likely that they're gonna put some irrelevant responses that don't make senses. And as they grow older, there will be less and less of the irrelevant responses. So we have this data table that tell you if the child's age is 2 and you give him, you know, a standardized test, it's likely that they'll have 15 irrelevant responses in there. And as they grow older, you notice the number of irrelevant responses go down. So it seems to be that there is a relationship between X and Y, X, which is the age, and Y is the number of irrelevant responses, but it's not positive, it's negative. As the child grows older, the number of irrelevant responses goes down, which it does make sense. Here's what I like you to do, guys. And you can do it, you know, just once and for all. I would like you to press the second key. I want to show you the scatter plot first of all. So press the second key and press Y equals. Now let me just clear this. Okay, and press enter now. Sorry, second and Y equals right here. And press enter. Make sure that on is selected right here. So let's say if you had off right here, for example, make sure to move it down to on and select that. And go to type and select the first one. The first graph is the scatter plot that we want. So select this one. And make sure, guys, your X list is L1 and L2. So I have L1 and L2, and I put my data in L1 and L2. So I'm good here. And now quit. Here's how you quit, guys. Second and quit. Clear. By the way, guys, if you are in stat edit and you don't see L1 or L2, don't panic. You can get him back. Look what you can do. You go to stat and just go to number 5, set up editor, enter, enter. And if you go back, you will see him. But I have him there anyway, so that's not an issue. How do you do the scatter plot? So after you've done this, I'm gonna repeat it, guys. Enter, turn plot 1 on. To turn it off, you just go to off and press enter. So I'm just gonna leave it on for now. And then this, and then L1 and L2 and quit. Look how can we see the graph. You just go to zoom and number 9. Here you go, enter. So this is it. Look at it and look at my graph. This one was done using probably StatCrunch. I did it, I don't remember, but this is the calculator. Now, you tell me, would there be a question probably on the final to find the scatter plot? Yes. I'll give you the data set and I'll give you 4 graphs and I'll ask you to select, you know, the graph that fits, you know, the data. So you need to do it on your calculator in order to be able to tell which is which. So this is the graph. Do you guys, would you agree with me that it seems like there is a relationship between the age of the child and the number of irrelevant responses, but it's a negative relationship. Would you guys agree with that?
Yeah.
Okay, good. Now let's find the value of R and see how strong this negative relationship is. So let me show you how to find R, guys. And you do it once and for all, unless if you reset your calculator, you have to do it again. So to find R, guys, watch. Do this first. I don't remember if I went through that last time. If I didn't, that's fine. We're gonna do it once and for all. So press the second key and press number 0 right here. You're gonna see this menu. So second and then number 0. And then I like you to scroll down, guys, until you see diagnostic on. I'm almost there. Okay, enter. Enter twice, guys. Okay, the diagnostic on is gonna, once you do this, I'll show you how to display the value of R. Okay, so we've done that. And now to find the value of R. All those steps, guys, that I'm talking about, you don't need to take notes. Are all listed in the handout. You see where I put here brackets, it says how to find the value of correlation coefficient. So if you guys forget, not a big deal. You can go back, just and do this if you're not doing it with me right now. So now you go to Stat, Calc, number 4, which is linear regression. This is our chapter about. And then enter, and here's R, negative 0.971 if you want to do 3 decimal places. And it looks very close to -1. And if R is very close to -1, the relationship is very strong but negative. So this is R. There is R square. Not only he gives you R and R square, he gives you the equation of the line of best fit, guys, which is Y equals AX plus B, and he gives you A and B. We will talk about this in a few minutes. So this is R, negative 0.971. So the next question, guys, was find the correlation coefficient and comment on the relationship between X and Y. Let me go to the next page. Using the calculator by following the steps above, R is negative 0.97. Let me put R here. Since R is very close to -1, there is a strong negative relationship between X and Y. X is the age, and Y is a number of irrelevant responses. Any questions, guys? So the next question I might be asking you is to find the value of R. That's very, very important that we know how to find R. Okay. C, find the equation of the line of best fit, the regression line. Use your calculator and the steps explained above to derive the equation. Well, guys, I still have the screen. So let me write down the equation for you. I'm just gonna write it on the side. It's already written, but I'll write it one more time. Y equals A. Let's round to 3 decimal places. So will be negative 0.963. X, it's AX plus B, as you can see on the calculator screen, plus B, which is 17.296. All right, this is the equation. Now, this is the equation right here. You notice, guys, that there is a hat on top of Y. We put the hat to say that this equation was generated from a sample, not from the population. So this is Y hat equal negative 0.963X plus 17.296. So this is the equation of the regression line. They call it the equation of the line of best fit, or it is called the equation of the least squares line, as you can see that. So if you are asked to find the equation of the regression line, or the line of best fit, or the equation of the least squares line, this is what you do, guys. You just find this equation. Now, this is what I'm going to show you. I want to go back to the scatter plot, zoom, and then number 9. And I want to go back to Y, and I want to enter this equation and see what happens, guys. Okay, for negative sign, you use this sign right here. Right here. This is the negative sign. So I'm going to enter the equation in this window right here. Negative 0.963, and the X is right here, guys, plus 17.296, and hit the graph. You see, this is called the line of best fit. This is the best line that you can draw and make sure all the points are as close as possible to this line. This is called the line of best fit, or the regression line. You can see it. You couldn't do any line better than this where it fits most of the points. The calculator gives you the best one. And this is what we call the line of best fit. Any questions so far? All right. I got 2 more parts and we will be done with this example. Now the important parts. So please pay attention to this before I do it. I'm going to do some explanation here before I get to the next question. Tell you why, what is the next question. All right. All right. So we found R. And R turned out to be, what did we say R was? Let me just make sure. Stat. Okay, it was negative. It was very strong value. Negative 0.9. What was it? Let me just. Okay, negative 0.97. And because this value, guys, was very close to -1, we were able to make a conclusion that there seems to be a very strong negative relationship between the age of the child and the number of irrelevant responses. But I like you to look at the data set here. This information came only from how many children? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 children. So we based, this conclusion that we make on the information we got from 9 children. The question is, guys, can we extend, just our finding, our conclusion to the entire population? Can we say in general that there is a relationship between the age of a child and the number of irrelevant responses? It seems like there is a relationship from the information that I have. But if I want to extend this to the entire population of children, can I say that in general, it is safe to say that there is a negative, strong negative correlation between the age of a child and the number of irrelevant responses? So now, guys, we're extending our work to the entire population. When we do that, just like we did in chapter 7 and chapter 8, we did a hypothesis test. We tested the mean, we tested the proportion. Now we're gonna test the correlation coefficient and see if we can extend this work to the entire population. So please pay attention to this and I'll show you how to do such a test. So R, guys, it's called the sample correlation coefficient. This is the hard part, guys. This is the hardest part. And then once we're done with that, we're almost done. So R is the sample correlation coefficient. And this came from a set of 9 students. No. There is a population correlation coefficient, guys. Which we can never find, just like finding the mean. We can never find the mean of the population. It is called rho. This is how we pronounce it. Rho. We need to study rho. If R shows that there is a strong negative correlation between the age of a child and the number of irrelevant responses, can we make, the same claim about rho, which is the population correlation coefficient? Since, guys, I cannot find rho by putting, just the X values and the Y values on the calculator, because in order to find rho, you need to have every single child, let's say doing it in the USA, you have to have every single child take a standardized test and record their responses. So you're talking about millions and millions, just of X, Y values, which it's impossible to get. So instead of finding rho, we can use the information from R to make conclusion about rho. So we're gonna run a hypothesis test on rho. And I'm gonna show you the 3 scenarios of running a hypothesis test on rho. Remember, when R is close to 0, we say that the linear relationship is weak. When R is very close to 1 or -1, we say that the linear relationship is very strong positive or very strong negative. So for testing the hypothesis on rho, we're going to have 3 scenarios, and I'll explain each one of them to you guys. Watch. Okay. Equal to 0, not equal to 0. That's 1. Rho equal to 0 means there is no correlation, because remember, when R is close to 0, the correlation is weak. This means rho is away from 0. It could be to the right of 0 close to 1, or to the left of 0 close to the -1. So here we have correlation. Let's do this. You could have this scenario, guys. This scenario means rho less than 0 means you are away from 0 to the negative. So this is a strong negative correlation here. Now, since this one has the equal sign, the correlation is weak here. So the null hypothesis is always the weak one, and the alternative hypothesis is always the strong one. You have the third scenario, guys, and I'm sure you can guess what the third scenario is. When you do a claim about this, you are testing if the correlation is positive. So this one, you test if the correlation is strong and positive. And this one, you test if the correlation is strong and negative. And this one, you test if the correlation is strong, but it could be positive or negative. So you either will be testing this claim, or that claim, or the third claim. Now, how can you tell? If he asks you to test for positive correlation, this is your statement. If he asks you to test for negative correlation, that would be your statement. If he asks you to test for correlation, that will be your statement. So your first step, guys, is to select the null and the alternative hypothesis. We don't put claim or no claim. This is what we put in those. Let me show you what we put. Here we put correlation is not significant, always. And for the alternative hypothesis, you put the statement correlation is significant. For this one, here you put correlation is not significant, correlation is significant. And the question usually, guys, test if the correlation is significant or not, if there is a positive correlation. So if there is a positive correlation, you'll be testing this. Negative correlation is that. Correlation is the first one. So here we put correlation not significant, correlation is significant. Correlation not significant, correlation is significant. So that should make it easy for you to state the null and the alternative hypothesis. This is a hypothesis test, guys. And a hypothesis test has 5 steps. This is the first step, stating the null and the alternative hypothesis. The second step is finding the test statistic, which is a t. The third step is finding the p-value. The fourth step, deciding to reject HO or fail to reject HO. And the fifth step, guys, is writing the conclusion in the context of the claim. So let me go back and show you the steps by using the calculator, and then I'm going to show it again by hand. So let's go back to the problem. There's the question, D. So this is the most important part here, guys. At the 1% significance level, test for negative correlation. You see what it says, guys? It says test for negative correlation. So here is how it's going to be. And here you say correlation is significant. I'll write it down again. It's written already in the handout. And here correlation is not significant. Again, if you forget why it's not significant here, remember there is an equal 0 here. And you know when you're close to 0, the relationship is weak. So no significance of the relationship. So we're gonna test this. You ready? You already have the data into your calculator. So let me show you how to run the test on the calculator. And I'll show you the 5 steps, guys. Okay, clear here. Oh, not this calculator, the other one. Go to Stat, Tests. Scroll up because the test that you want is at the bottom. And can a student tell me, given the title of this chapter, which test is it gonna be? It's the only test, one test only for this chapter. Which one would you pick? What did you say?
The Lin Reg T test?
Yes, linear regression t-test. Exactly, that's the only one. Very good. And this one, guys, is gonna give you everything. You will see. So I'm just gonna listen to you and go down to this one. Oops, sorry. So I'm gonna select this linear regression t-test. Watch, guys. Okay. It's asking me, is my data in L1 and L2? I'll confirm that. Don't touch the frequency, guys. You touch it, you ruin the entire problem. That's a 1. Okay. Now it's asking me for the alternative hypothesis, just like in the previous tests. Okay, your alternative here, guys, is less than 0, remember. So I'm gonna select that. Just to make sure it is selected. Okay, and just calculate, watch. Okay, T, step number 2, it's negative 10.74. I'll write it down here. So that's step 1, step 2. T is negative 10.743, 3 decimal places. P-value, guys. P-value is, let me see, probably I made a mistake here. Oh, I put row greater than 0, sorry. I thought I did change this one. Probably we weren't very careful. Oh, okay, I selected the wrong one. Okay, we fix it. Now it's fixed. But p-value was huge, that wasn't right. Okay, T is negative 10.743, and look at the p-value. I write it down, 6.656 E negative 6. Okay, let me just put this on the side and explain this. This means, guys, you have to move the decimal place 6 digits to the right. So I think you agree with me, it is 0, which is less than alpha. Then you reject HO. And if you reject HO, here's what you say, guys. It's only one of 2 statements. If you reject HO and the significance of the relationship in HA, you say there is enough evidence at, what was alpha here? 1% level of significance. To conclude that correlation is significance. To conclude that correlation is significant between the age of a child and the number of irrelevant responses. On a test, on a standardized test, actually. There you go, it's right here. Now, if you fail to reject HO, guys, all you need just to put the word not here. So you say there is not enough evidence to conclude that correlation is significant. So either there is enough evidence to conclude that correlation is significant, or there is not enough evidence to conclude that correlation is significant. And these are the steps: step number 2, step number 3, step number 4, and step number 5. And this is with using TI 84. As I said, since that was the practice of previous chapters, you will be able to do this using technology by finding the p-value and making a decision based on the p-value. Any questions about this part, guys? Feel free to ask questions. After I'm done with this example, I'm going to do another one. I still have a couple parts of this example. Let me see if I have any questions there. Okay. All right. Let's continue. Just 1 second. And I'm going to show you how we could have done this in a different. The test statistic, guys, is T, as I told you, and this is the formula for T. It's R divided by the square root of 1 minus R squared divided by N minus 2. So if a student attempted to do this one by hand, you would get pretty much the same answer. R was what? Negative 0.97 divided by square root of 1 minus negative 0.97 squared, N minus 2. N is how many children or how many in the study? There are 9 minus 2. And if you do the math, guys, you should get pretty much, the same answer. It might be slightly different from this answer because you're rounding here, but it's okay. It will be different, but not by much. So this is another way to find the test statistic. Okay. And I did explain to you guys and how to run the test. So it is a linear regression t-test. Let me go back to the test and show you what's hidden there. Actually, there is more than just what you got. So you got the T, you got the p-value, degrees of freedom here is n minus 2, which is 9 minus 2, 7. And look, this is the equation of the line, but he writes it here. The guy who created this program decided not to do ax plus b, to do a plus bx. So if you guys wanted to get the equation of the line from this screen, you make sure it is a plus bx. Your a is 17.296, and what's b? B is negative 0.963. So if you write it down, you write it as 17.3 minus 0.963, and it's just going to be exactly the same as this one, guys. Look. But the one we got it here, it says ax plus b, whereas this formula here uses a plus bx. They're exactly the same, but they swap the values of a and b. So make sure whatever screen you use, just follow the prompt, of the equation there. Here it is a plus bx. So this is the equation of the line. And the conclusion, as you notice, there is enough evidence at the 1% significance level to conclude that there is a negative significant correlation between X and Y. Well, actually, I went one step further and I said what X is between the age of a child and the number of irrelevant responses. Okay, let's go back to the next part. Now, you should be able to help me do this now. Part E. Find the predicted number of irrelevant responses when the child's age is 8. How do I do this? Let me just write the equation one more time and see if you guys can help me with that.
Would you put 8 where X is?
Exactly. It's algebra. If you guys, you heard the student. If he asks you, find, you know, the number of irrelevant responses when the child's age is 8, you simply just replace X with 8. And if I replace X with 8, it will be right here, times 8 here. So then 9.596, which is approximately 10 questions. So 17.3 minus 0.963 times 8, just do the math. So this is how you do that. This mainly just an algebra question. He gives you the X value, plug it in the equation and find the Y values. And sometimes, guys, I might give you the Y value and ask you to find the X. So if I give you the number of irrelevant responses to be 12 and I ask what's the age of a child, you just plug in 12 right here and then try to solve for X. Subtract 17 from both sides, divide by negative 0.93, just mainly an algebra question. Okay, so that takes care of this part. But let me go back to the data set. The ages here, guys, fluctuate from as low as of an age of 2 all the way to an age of 12. And when I ask you find, you know, the number of irrelevant responses when the age of a child is 8, you know 8 is between 2 and 12. What about if I ask you to find the number of irrelevant responses if the age of a child is 14? So if X is 14, how do you guys think that we're gonna do this? Any ideas? This is the equation. We have the equation already. Would you plug it in? Yes or no? Where X is. So I'm gonna just go back to the next page, second page that we worked on and change the answer from 8 to 12. What do I do here? If this was a 12. If this was a 14, for example, I said, if this was a 14, guys, you could not use the equation to find the Y value. And let me tell you why. Because everything we did was based on the studies of children whose age was as low as 2 and as high as 12. If you go beyond the 12 or below 2, you will not be able to use the equation. So this equation will not be valid to find the number of irrelevant responses. It is only valid to find the number of irrelevant responses if the X value is confined between the lowest value and the largest value in the data set. So in the book online, when you do your homework, when he gives you an X value that doesn't belong, you know, just between the minimum and the maximum values of X that are given to you, you will state, you know, just an answer not meaningful, that you cannot do it. But if you need to do it, here's what we can do to find the Y value when X is 14. So if X is 14, guys, which is not between 2 and 12, and when I need to find the Y value, I cannot use the equation. But look what you can do. You can estimate it. Take the average of those values and use it as the answer for X equals 14 or 15 or 16, whatever. So if you take 15 plus 15 plus 12 plus 13 plus 11 plus 10 plus 8 plus 6 plus 5 and divide it by 9, you can arrive at an estimate to the Y values. But to plug in X equals 14 into the equation, it's not correct. You cannot do that. But if I give you X equals 7.5, yes, definitely plug it in because 7.5 is between 2 and 12. If I give you 10.5 age of a child and I ask you to find the number of irrelevant responses, definitely you can do it by plugging it into the equation. But anything goes above 12 and below 2, you could not use the equation. Okay, so that's E. Now F. Find the value of R squared coefficient of determination and explain it. So I'm going to spend the next 5 minutes explaining R squared, and that should be it for this chapter. We'll do another example right after this. So let me tell you something about R squared. You already know R squared, since R is, and the calculator display the value of R squared. So R is negative 0.97. R squared, guys, simply square this one. So if you square it, what do you get? And calculator shows this value anyway. It's 0.941. Okay, let me explain what R squared is, guys. Okay, I'm gonna give you this example to better understand R squared. Diamond, weight, and price. You guys agree with me that as the weight of diamond increases, the price increases as well. For example, if you have a 0.25 carat, you might pay $500 for a diamond. If it is 0.5, it's gonna go probably to this price. 1 carat, it's gonna be more expensive. 2 carats, it's gonna go probably to 5,000. Just making up, you know, just that. So would you guys agree with me if I tell you that there is strong positive correlation between the weight of a diamond and the price? As the weight increases, the price increases. I think all of us would agree with that. So let's say, for example, I find R, I have some data, weight and price of diamond, and I find R, and it turns out to be 0.86. That's R. What I like you to do, guys, find R squared for me. So that will be 0.86 squared. Okay, let me do this one. It's a 0.7396. I'm gonna make it 0.74. I'm gonna change it to a percent, so it's 74%. Let me tell you what the 74% is. What does it mean in this case? The coefficient, R squared is called the coefficient of determination. This is how you interpret it. You say 74% of the changes in the price of diamond can be explained by the change in weight. So 75% of the time, when the price changes, it is due to the change in weight. But it's not 100% of the time. There are some other factors, guys, that change the price of a diamond. And can you share those factors with me? There are some other factors, hidden factors that I didn't mention here. We only mentioned the weight here. Can you guys think of some other factors that would change the price of diamond? Give me some other factors.
The shape.
Shape, that's one. What else? I see a chat here in the box. Purity, excellent. Yeah, they call it clarity. Okay, there is another factor that I think it's very, very important also. What is it, guys? So the shape, the cut, the purity, clarity of the diamond, and there is another factor that's important. Size.
If it's man-made.
Okay, what else? Quality, yes, the quality of the diamond. These are the factors that determine the quality. We're assuming we're not doing, you know, cubic zircon. We're doing real diamond here. What do you guys agree that the color is important as well? Color. So these are the hidden factors that our relationship did not manage, you know, just to touch on. Our relationship is solely between the weight and the price, guys. But there are some other factors that determine the price of diamond. So 74% of the time, the change of the price can be explained by the change on the weight. But 26% of the time, the change of the price can be explained by the shape, the purity, clarity, the color, the cut, etc. So the coefficient of determination will explain the change of the price due to the change in weight, and that's what the coefficient of determination is. If this was 100%, guys, that means the price is solely based on the weight, but that's not going to be 100% because the price of diamond is not only determined by the weight, it's determined by other factors as well. So look what it says here for if I go to F. Find the value of R squared and what does it mean? So R squared is negative 0.97 squared, which is 0.94. So you say 94% of the variation or the change, I use the word change here, in the number of irrelevant responses on a standardized test can be explained by the change in the age of the child. So 94% of the variation in the number of irrelevant responses on a standardized test can be explained by the variation. Variation means change, guys, in the age of a child using the regression line. So the value of R squared is called the coefficient of determination and represents the percentage of the amount of variation in Y that can be explained by the amount of variation in X. So you always start with Y and then relate that to X. Any questions here, guys? We're going to do another example so you can have another feel of this relationship. All right. Let's go to the next one. Okay. What I'm going to pause the recording right now, guys, and I'm going to have you enter those values, example 2, X and Y. L1 and L2, please. Of R. Okay. So let X represent the average annual hours per person spent in traffic delays, and let Y represent the average annual gallons of fuel wasted per person in traffic delays. You can agree, guys, that there is a relationship between waiting in traffic and the gas wasted, because if your car is, the engine is running, it's gonna waste gas. So the first question is find the value of the correlation coefficient R, and here you go. I go to stat, calc. If I don't want to run a test yet, linear regression, AX plus B, and here's R, 0.794. You must have second diagnostic on in order to see R. If you don't see it, just later go back and do the second and then zero catalog and go to diagnostic on. Okay, so R is 0.794. At the 1% significance level, test the claim that rho is greater than 0. Okay, so significance correlation. So this is your HO and HA. Here you put correlation is significant. It's always is significant in the alternative and not significant in the null. Correlation, not significant. So then it will remind you what to put in step 5. All right, so let's run the test. Stat, tests, scroll up, linear regression t-test, enter. Sorry, my phone is L1, L2. And we need to test for positive correlation, so greater than 0. And hit calculate. Here you go. T is 3.204 and P value is 0.0093. There you go. So T is, let me just write it down. 3.203, and the p-value, guys, is 0.0093, which is less than alpha. You reject the null hypothesis and conclude there is enough evidence to conclude that correlation is significant between the number of hours spent in traffic delay and the number of gallons wasted. Part C, predict the number of annual gallons consumed when X is 30. Now look at X equals 30. Is it between the lowest and the largest value here? What do you guys think? Is it safe to plug it in into the equation? Yes or no? It is safe to plug it into the equation because 30, guys, is less than 35, which less than 42, which is the largest value. So you just plug it in. And here's how you do it. You put y hat equals, okay, we need the equation first. Well, the equation is right here, guys. Y equals a plus bx. I'm gonna use the y equals a plus bx if you like. So that will be, let me just write the equation. What is a? 2.81 plus b. And what is b? I need to scroll down to see b. 1.444. Okay. And now to find the number of gallons wasted, just plug in x equals 30. 2.81 plus 1.44 times 30. Okay, if I do the math, plus 2.81, 46.01 gallons. Okay, so what about if I ask you to find R squared? What is R squared here? And then I'll explain it to you and tell you what R squared is. So R is 0.794. What would be R squared? Let's see. R squared, 0.794 squared. Okay, I got 0.6304, guys. If I want to interpret this, that's the important part, to learn how to interpret this. So 63%. You can say 63% of the change in the gallons wasted in traffic can be explained by the change or the variation in hours spent in traffic delay. So it's not only the hours that you wait in traffic delay that determines how much gas is wasted. There are some other factors, guys. Can you tell me about some factors that could cause more gas to be wasted other than just waiting in traffic delay?
Speed increase.
Okay.
Weight of the vehicle.
Exactly. If you have an older vehicle, guys, if you have an older engine, it might, just consume more gas than other, whether it is a V6 or V4 or V8 engine. So there are some other factors other than just waiting in traffic. Very good. So this is what R squared means. Okay, guys. I'm gonna leave this exercise and show you, just to show you the next exercise, very much the same. Sketch the scatter plot, test for positive correlation. So here, HA, rho is greater than 0, rho is less than 0. Correlation is significant, correlation not significant. Find the equation of the regression line. You can see very much the same question. What would be the number of absences in a given day if temperature is 95? So you just have the X value is 95, find Y. Find the coefficient of determination R squared and determine its value. There are a couple more things I want to discuss with you before I wrap this chapter up, because you might have those questions. So just one sec. Okay. When I ran the test, just the previous one. Let me go to the previous one. L1, L2, we did greater than 0. We hit calculate, and let's walk you through this. So guys, this is what you get. You get the test statistic. You get the p-value. Degrees of freedom is 6, means the sample size was 8. It's 8 minus 2. You get the equation of the regression line, y equals a plus bx, but put a hat on top of y because it says came from the sample. Okay, you get s, which I'm gonna talk about right now. You get r squared, and look guys, what you can get also r. So you get everything when you run the linear regression t-test. Let me tell you what s is if you are asked to find s. S is called the standard error of the estimate. It is the standard deviation of the observed values. The observed values, guys, are these values right here. That's given. These are observed because we take, we watch people. We take, you know, just notes of people who spent 20 hours, how many gallons they wasted. The ones who did 4 hours, how many gallons, etc. So if you are asked to find this standard error of the estimate, you will run the hypothesis test, and then it is S. S is 16.51. Now, here is another way, guys, to run a hypothesis test rather than doing the linear regression t-test. And he might ask you in the book, you know, to do this, which is a much simpler way to find out whether the correlation is significant or not by just doing this, which will take me 1 minute to explain. So just give me 1 second to take you to this one. All right. The correlation is significant when the absolute value of R is greater than the value in the table. Let's say he asks you to test, and if you see this table, guys, in the homework online, you just use it. And I'm going to show you how easy it is to use this table to determine whether correlation is significant or not significant. Remember, we said the conclusion is either there is enough evidence to conclude that correlation is significant or not enough evidence to conclude that correlation is significant. So either yes or no. If let's say you came up with R and R turned out to be negative 0.95, what would be the absolute value of R? Absolute value is writing R without the sign. So do you guys agree there will be 0.95? And let's say N is 10. He gives us a set of 10 and alpha is 5%. So look what you do to find, to tell it quickly without going through the steps of the hypothesis test, whether the correlation is significant or not. Look what you can do. So let's say he gives you N. So using the critical value for the Pearson correlation coefficient table, table 11. Let's say N is 10, and let's say alpha is 0.05, and let's say R turned out to be this. And you wanna study if correlation is significant or not. Look what you do. You find the absolute value of R first, which is 0.95. Keep it in mind now. Now we'll go to the table, guys, and we'll find N equals 10 and alpha is 0.05. So N is 10, alpha is 0.05. What's the value? 0.632. This is called the critical value. Okay, look what it says. The correlation coefficient, correlation is significant if the absolute value of R is bigger than the critical value. Okay. What is the absolute value of R in my case? It's 0.95. And you guys agree that it is bigger than the critical value, then you can make a conclusion that correlation is significant. It's as simple as that. But if he asks you to run the hypothesis test on rho, these are the 5 steps that we just did. But just using the critical value approach with this table, you simply find the absolute value of R and try to match it with the critical value. If it is bigger than the critical value, you say correlation is significant. If it is less than the critical value, you say correlation is not significant. So let me just make another one up. Let's say R is negative 0.65 and N is 12. So what's the absolute value of R will be 0.65. Now N is 12 and alpha is 0.05. So let me see what the value would be. It's 0.576. Well, 0.65, guys, is still bigger than 0.576. So you can say that correlation is significant. So this is everything that you need to know in this chapter, guys, that will be pretty much it. I got the handout. It has all the details that you need to know in chapter 9, and you should be able, to do the homework of chapter 9 after this. I just need a few more minutes, guys, to go over something in section 10.4, and we should be able to wrap this up. All right, so I need 5 more minutes, please. Let me tell you what section 10.4 is about, and then I'm going to do an example next time we meet, and then we'll have 2 more sections. We should be able to wrap them up tomorrow. So just 1 second. You know what, guys? I think you've had enough. I can handle this tomorrow. It should take us about 5 or 10 minutes to cover section 10.4 tomorrow. So it will be the first thing to deal with tomorrow, and then we'll do 10.1 and 10.2. So you're all set.
Thank you.